Welcome to STEM Simplified, where we break down complex physics and math into simple, easy to understand lessons. Subscribe, like, share, and turn on the bell for more tutorials like this. In this series, we are diving deep into digital electronics and analog electronics plus devices, a core subject in electrical, computer, and electronic engineering. Whether you are a university student, diploma student, or a tech enthusiast trying to master how digital systems really work, you are in the right place. Today we start from the very basics. Analog versus digital signals. Have you ever wondered why old radios sounded different from your modern smartphones? It's all about analog versus digital signals. In this video, you'll finally understand the core difference between the two and where each one is used in the real world. Welcome to the Digital Electronics and Devices series, and today we're diving into the very basics, analog versus digital signals. Let's get started. First, what is signal? A signal is just a way of carrying information, usually by changing voltage or current over time, as shown below. This information can come from your voice, temperature changes, sound, or data, and how we represent it defines whether it's analog or digital. We're going to start with analog signals. Analog signals vary smoothly and continuously over time. They can take infinite values within a range. For example, the sound of your voice traveling through the air, the reading on a mercury thermometer, or the signal in an old radio. These all are analog. Devices like cassette players, vinyl record players, and old rotary phones all used analog signals. Why did we use analog? Well, analog signals are natural. They represent real-world information in its pure continuous form. But they are not perfect. They have two major drawbacks. First, they are prone to noise. Small disturbances in the environment can distort the signal very easily. Second, they are harder to store and copy accurately. Each time you copy an analog tape, some quality is lost. Now let's look at digital signals. Digital signals are not continuous. They use discrete steps, typically represented by just two values, zeros and ones. The figure below shows a square wave highlighting the jumps between 0 and 1. This system is called binary, and it's the language of computers, smartphones, and most modern electronics. Examples of digital devices include mobile phones, digital watches, laptops, flash drives, and basically everything around us today. Why is digital better in many cases? Here is why. Less affected by noise. A signal that's either 0 or 1 is easier to detect even if there's interference. Easier to store and process. You can copy a digital file 1,000 times and never lose quality. Number 3. More compatible. Digital signals work seamlessly with microcontrollers, processors, and storage devices. Of course, there are downsides. Converting from analog to digital introduces a tiny bit of inaccuracy. This tiny bit of inaccuracy is called quantization error. And since the real world is analog, we often need special converters to go from analog to digital and vice versa. As you can see, analog is more natural but harder to control, while digital is more stable, efficient, and dominant in today's electronics. Why is digital dominant today? Okay. In the early days of electronics, most devices were analog. Think of volume knobs, cassette tapes, vinyl records, all representing information with smooth electrical waves. But engineers ran into problems. Analog signals distort easily. A small amount of electrical noise could ruin the quality. Storing and copying analog data degraded it over time, like a cassette tape wearing out after many plays. Then came digital technology, where information is stored in binary code, ones and zeros. That changed everything. Digital signals are more reliable. They can be transmitted and stored without degradation, easier to process and analyze, perfectly compatible with computers, logic circuits, and AI systems. Think of the difference between an old cassette tape and an MP3 file. One fades over time. The other stays crystal clear no matter how many times you play or share it. So, to wrap up, analog signals are smooth, continuous, and natural, but they are sensitive to noise. Digital signals are strict, precise, and dominate modern electronics because they are easier to understand, to handle, to store, and process. In our next video, we'll dive into the energy band theory, where we'll uncover how materials conduct electricity at the atomic level. If you found this helpful, give it a thumbs up, subscribe, and tap the bell so you don't miss the next tutorial in the digital electronics, analog electronics, and devices series. Have a nice time. See you next time.